All right, let's get started. Good morning. Yeah, pass the homework assignment here. The solutions and the handouts are on that side. Right. So for the exam on Friday, we'll have whatever we covered till today, right? Including modules 1 and 2. So it won't focus on that. Right. Just because we're not covering it, this module doesn't mean that you have to forget those stuff. So it might be sort of in there, right? I'm going to be out of town on Friday, so the TAs will be here. So if you have any questions about the exam questions, write down your assumptions and answer those, right? So this time I'm going to give 7. You have to do 6 of 7, right? So if one of them was not clear, you can ignore them, right? So are there any questions about what you covered so far? We're kind of going sort of slow because this chapter is taking more time than I suspected. But that's okay because like I said, the first 4 modules are more important than the last one because last one ties them together. But you need to understand what's going on here, right? So there's a lot of stuff with the memory management and stuff which you kind of get it from other areas like compilers and stuff. So essentially you kind of see where the operating system is in a point, right? So there's something that hardware gives, there's something that the program wants. Program wants to have this notion of areas and memory allocation and stuff like that. And the hardware has to give you some things, and depending on what the hardware can give, you can do better or worse, right? So we looked at different techniques. One of the notion of a logical address and a physical address, and most of these things are driven by what the memory management unit can do, right? So when you want to do paging, we left off sort of at this picture where we had we take the address, split it into a page and a descriptor and a displacement. And the page size is decided by the hardware. So depending on what the hardware supports as a page size, actually frame size, you would allocate a certain number of D bits. So it's up to the operating system to fill up the page table, right? And if you think about it, every memory operation now will have to go through this page table. That slows things down, right? So all these things are in the way of getting good performance for your program, right? If you could generate the direct physical address in the program itself, you wouldn't have to go through this translation, which means that you wouldn't have to do an extra memory read, right? So if you do this stuff, now you have to do 2 memory reads, one to read the page table, another one to get the actual content. And you can't even do them in parallel because you have to wait for this to finish to get the address of where you want to go, right? So for folks who are taking hardware architecture course, you'll notice that most of the complexity of your hardware goes into stuff like this, right? To make the stuff be more programmable, more usable by system users and stuff. So one of the ways that they optimize this is this notion of a TLB, right? From an OS perspective, we don't know what TLB is, we don't know how to manage it and all those things because it's managed by hardware. Essentially what it does is it keeps you would think the most popular or recently used addresses into this cache, right? The nice thing about this cache is it's associative memory, which means that you do a parallel search. So if you look at this little arrows up here, right? So associative memory means that you can look it up parallelly, right? So if you have a page you're looking for, the hardware maintains the page number and the logical address in this cache. So it can look at them parallelly. So if you have like 1000 entry TLB, then it can see if all the 1000, if it's in one of the 1000 elements, and if it is, it can release the frame number from there, right? So if you think of other ways of searching, like binary sort or something, the amount of time it takes depends on the array size, right? So if you do a binary search, you have to find the midpoint. You basically have to search. So when you do associative search, the search is really fast. So essentially, you add a little bit extra to 0, right? Essentially, you want that to be fast. And if you can hit in a TLB, you're good because then basically you are operating as if the address generated can be translated instantaneously. If there's failure, then you come to the page table, right? But as far as operating system concerned, we can only operating system fills this table. Who fills the TLB is the hardware, right? We don't have control over it, but it affects the performance, right? how it affects the performance is you can think of it as a simple math operation, right? So if you assume the time for associative lookup is little epsilon, right? If you assume that the time to do memory operation is 1 microsecond, you have to know what the hit ratio is, the ratio of accesses which are going to the associative and the ratio which actually goes to the main memory. So if the hit ratio is alpha, which is given to you, or you kind of find out sort of what you do for the homework project 3, right? So essentially, if there is a hit, right, you take 1 microsecond, which is the time it takes for you to get the memory, plus this little epsilon, because you have the associative memory, times alpha. If that fails, you do the 1 minus alpha times 2 plus epsilon, because you still have to do the memory lookup for the page, memory lookup for the actual contents, plus the associative cost, right? So you come up with this little cost, right? So if you do the numbers, if you do how these things work, this can so if the alpha was really small, it can significantly bring your performance down, right? So you can have the fastest processor out there, but if you're not hitting the TLBs, then it hurts, right? So this is, from the architecture perspective, this is one thing which differentiates between the different processors. If you go in the market, right, if you look for processors, you may find a 2 gigahertz processor for laptops, 2 gigahertz for servers, and 2 gigahertz for real servers, right? The real servers tend to have a lot more of these TLBs and stuff, right? They may have the same, they may look like they have the same performance, but they have these things which make the stuff faster, right? So for example, the Itanium ones, right? The EXPC server 4 and stuff, they're, I think, 1.6 gigahertz processor, right? But if you run tests on those systems, they actually can keep up with your normal, the fastest Xeon and stuff, because they are, even though they're only running at 1.6 gigahertz, it's a different architecture, but still they can keep up with this stuff because they have good stuff like this. They have a lot more TLBs and stuff, right? Those machines are very expensive. I mean, they were quoted as 80,000 for the EXP server 4, and server 2 was 40,000, right? Essentially, most of the cost goes to stuff like these. So that's one of the things. Most of you may not look at those when you buy your laptop. Most of you, how many of you look at the TLB size? It's kind of hard to get it out from the manufacturer too, because they don't like to advertise those stuff. But they have a very significant effect, and if you don't get the hit ratio, you really suffer, right? So the question is, how do you affect the TLB hit ratio, right? How do you get better TLB hits, right? We don't know how the TLB entries are filled up, right? But it will have to be something based on something in the past, right? The hardware does not know anything about the future. So it's going to have to look at the past to figure out what you might want in the future, so you can keep the ones that you really want in the future, right? This is the second part, right? How do you think you can write code which will be giving you good TLB performance? It's not operating system perspective, right? Operating system only fills the page table, and the hardware does its replacement. The real performance gains can be gotten only by the application program, not by the operating system, right? So thinking about how the TLBs may be populated, what kind of a code do you think will help you with TLB hits? Would it be suppose I have small program, right? And then suppose I have in terms of code, which one do you think would give you a good TLB hit ratio? So let's see what would really, we don't know what assembly language is, but let's assume what assembly language might do, right? So it will have to do something like if 1, right? So like at a lower level, right? It'll do assign memory address A to 1, and then it'll go to, let's say this. something like this. You'll have to do some sort of a comparison, and if the comparison is true, you'll do this, and then you'll do a goto, right? So in assembly language, this is sort of what your program will become, and this will sort of be like what it is, right? So there'll be address of A, address of B, address of C, right? So for TLB hits to happen a lot, you will have to keep addressing the same address over and over again, right? The more you use it, the more likely it's going to be in the TLB, the more likely you're going to have a hit, right? So which one of these programs would help you?
The second one.
This one? Yeah, so depending on how your program is, right? So you expect this, since you keep going to the same thing, the instruction of the address of these things remain the same. So this program will actually work faster than this one. The first time it will take the same time, but the second time you'll have a lot more TLB hits, right? So that goes to how you write your program, right? Operating system has no control over what you do, but if you're aware of this stuff, you may want to write your code in a certain fashion where you use this TLBs, which you don't know what it is, you don't have control over it, you can't see what it is, but you see better performance by doing this, right? So this is for instructions, right? So for data, what kind of data structure do you think would be good? Integer A or now you're looking at the data accesses, right? Would accessing a matrix be better than accessing a single variable? Let's go deeper, right? If you access a matrix in a certain fashion, right? So for example, we do, let's say, I think we looked at it before in some other context. So for we looked at this program before, right? Whether we flip this row and column, right? Do you think this really matters for the TLB stuff? The order of how you do it? So the matrix is going to be 0 to, let's say, 100, 100, right? Do you think it matters that you traverse the matrix like this or you traverse the matrix like this? If you go by column, you're going like this. If you go by row, you go that way, right? Do you think it might give you, it might help you or hurt you? Yes?
Horizontally, you're just going into contiguous mapping, but if you go down, you'll be skipping all over it.
So what would happen is you cannot store a two-dimensional array in the computer, right? You have to translate that into one-dimensional array. That's how it's stored, right? So somehow it has to be stored as a one-dimensional array, right? And somehow you have to do this mapping from here to here, right? And the one that Adele talked about was if you assume that it's a what's called row major organization, that means the first row would be here, and then the second row would be here, and so on, right? Fortran does it the other way. So C does it this way. Fortran does it on a column basis, right? I don't know how many of you use Fortran. Fortran is a scientific language which has been there forever and ever, right? But Fortran does it in the column fashion. So first column, second column, and third column, and so on. But C does it this way, right? So if you have this kind of arrangement, and if you're going through the matrix in a row fashion, what do you think there'll be good TLB hits? you'll be accessing this way, right? You'll be accessing, let's say address 1, 101, 102, 103, and so on, right? This address keeps changing, right? So why would you still expect to have TLB hit? Yes?
So they all be on the same page?
Yes. So now the paging stuff comes in, right? Even though you're going through different addresses, the page number is likely to be the same, right? So you're going through the whole page number before you go to the next page number and so on. So you're going to have a good performance if you go this way. You're going to have a terrible performance if you go the other way, right? And that you cannot really predict, but you'll notice it. If you run this program, if you switch the way you access it, yeah, I think you could go like a couple of times, orders of magnitude speed difference if you go one way or the other, right? And so in essence, all that TLB does is it's trying to get good performance out of the whole thing. It's done by the hardware folks. So if you're doing a hardware architecture stuff, they provide this TLB, but they can't really do anything unless you program it to use that, right? So if you wrote programs which went the other way, right, because you can you can change this and this way, either way, to get the same code performance, right? If you do that, then your hardware is not going to get good performance. Intel cannot do anything about it. Your operating system cannot do anything about it because that's how you're accessing. But you're understanding that all these things happen, that you have pages, there's TLB and all those things, would tell you that if you ever see a code like this, right, you're going to say, no, flip this other way because you're not going to get good performance, right? Because you're going to fight the TLB, you're going to be opposite of what the system wants. So that's essentially how these things happen. So you understand what the hardware can do, understand what the operating system can do, but the ultimate responsibility is with the user. And the next component is all this stuff of a page table, TLBs, and everything is assigned to a given process, right? You can't share a page table between two processes unless you know what you're doing, unless the operating system gets involved and stuff. So when I do a context switch, I have to make sure that the new process, the new process will look at its own page table, right? Which means that it will have to have its own cache. It can't use the same TLB cache from earlier time, right? So if you have one process which is using a TLB and you context switch it and bring another one, you can't leave the same TLB cache for the new process, because what will happen is the new process does not know that. So all you have right now is page number and the logical address, right? So if the new process issues a page number which happens to be what the old process used, then you're going to translate that to a logical address which was in the old process, right? Which is not a good thing. So you can do one of two things. One is you can either flush the TLB, which is a simple thing to do. So every time you do a context switch, you flush the TLB, right? What does that mean? What will happen if you flush the TLB every time you do a context switch? How would you see that in your program? So when you context switch your program back in, you'll have to start all over again. It'll have to. So you don't actually store it anywhere. So when you come back, you have to start learning again. So once you context switch in, for the first few instructions, you'll have to pay the price of filling the TLB back, right? Which is not a good thing. You don't want that, right? The other way is to, if the hardware supports it, have some sort of an ID, right? Does not matter what it is. You basically have to tell the hardware the current process ID is, let's say, 1, right? Any TLB entries which have this same ID of 1, you can use. If the ID is different, then flush it, right? So again, these sort of things come in when you go to a server kind of stuff. The desktop processors don't do this. They just flush the TLB. On a server kind of processor, they have this notion of ASSID or whatever, right? Some sort of ID to tell the hardware, I have this notion of process, which you don't need to know. But all you need to check is if the ID that is on the TLB is different from what this process is, then flush this stuff. So it doesn't have to flush everything. You just flush it on the demand, right? It makes more sense, especially if you have the TLB which is large. The larger the TLB gets, you don't want to waste all the stuff that it learned. So you want to have this complication. So if the hardware can support that, we can use that. If not, you'll have to flush the TLB every time, right? So going back to the context switch from module 1, right? context switch now adds one more cost. Context switch, you need to store all the register values into the PCB, right? All the state into the PCB. You'll have to change the page table to use the new one, and you have to flush the TLB, right? And flushing the TLB is really awful because now you forgot all the things you learned, and the new one has to relearn all the things. So if you make the time smaller and smaller of how soon you want the next context switch, the less time you have to learn, less time you have to use the TLB. So that's the performance hit you'll take, right? Does that make sense? So in the last lecture, I kind of alluded to the fact that if you have a page table and the page table entry was invalid, you store something which is invalid there, right? In which case you can get some sort of a segmentation fault or whatever, right? So you can either do that by saying if the page number is -1, right? If the frame number is -1, then you get a fault, right? Which means that you can't use that one frame number. So most of the hardware gives you an option to have a validity bit, right? Which says that in the page table, now I can use one bit to say whether it's valid or not. So when the operating system loads the pages, it can load all the pages that it knows there has to be a mapping, marks all those bits as B, and the ones that it doesn't want you to use, will change it to invalid, right? So sort of like this. So in the page table, rather than just having the frame number, you also have this one bit which says whether it's valid or not, right? So if it's invalid, then regardless of what is here, the hardware will generate a segmentation fault, right? So this is a very powerful technique. This basically allows the operating system to say certain pages, it can change the bit so that it will be invalid, in which case you get an interrupt back, right? In this case, I'm using it to say whether a page is invalid or not, and we'll see later on we can play lots of tricks with this stuff, right? This is a very powerful tool which basically gives the operating system control over some pages, right? So in the more advanced hardware, you not only have this in I or B, you can also have whether it's read, write, execute, and whatever, right? So you can say, give me a fault if the page is doing something that I didn't want it to, right? Give me a fault if it's a text. If I call this a text and you try to modify it. Give me a fault if you call it read only and you try to modify and all those things. And we're going to use that for paging and stuff we'll see in the next chapter. But essentially this is one powerful way for the operating system to get involved, right? Otherwise, you set the page table, you let the hardware go, and the operating system does not get involved till the timer goes off or whatever. This is a way for the OS to get involved. Again, it's all possible only if the hardware allows it, right? So if you buy a really powerless MMU, it may not let you do all the stuff. But you may have a good MMU which will support all the stuff, which also means that when you do a context switch, I have to set the page table, I have to set all the bits in the whatever I want it to. That makes the operating system a little bit more complex, right? Make sense? But we'll get back to this because this is a very, very nice way to do a whole bunch of things that we like to do. And the other thing I kind of alluded to was the fact that how big the page table could get, right? So one way to optimize that is I think in the last lecture we looked at what happens if you have a certain number of page table size. Your page table size could be few megabytes. But if you think of a 64-bit processor, which is what most of the machines are going towards, it's going to become extremely big, right? So if you assume a 64-bit address space, if you assume 8K page table size, then essentially you're looking at 2 times 10 power 15 page table entries, right? Even on the 32-bit address space, if you have to have, let's say, a page table of 16 megabytes, right? It's wasteful because even for a hello world program, you have to use that big a page table size. So you could make that smaller by saying, limiting it to certain, how big the page table should be, right? And that's one optimization. You could say this process can only have a page table which is size of 10 or something, which means that you're kind of stuck with the size, right? You can't allocate more memory than what the page table was without going through a mess. So that's one problem, and there are multiple ways to solve this stuff, right? And all of them adds more complexities. all of them have to have hardware involvement, because like I said, you set up the page table, and then the hardware is supposed to take over. So the operating system is not involved in all of those, right? So it has to use the hardware. So depending on what the hardware provides, it can do any of these operations. And all of them are trying to optimize on how big the page table should be. All of them add complexity, which will slow your processor down, right? And this is one of the things that companies like Intel and all have to wrestle with, right? A general purpose operating system has to deal with all this kind of issues. They have to be able to access as much memory as possible. And as we'll see, each of the operations add more complexity. So the hardware chip takes more and more of this kind of stuff, which is sort of overhead. From the hardware perspective, you just let it run as fast as possible, but you can't because you have to add all this overhead, right? So the first way to attack this problem is through a notion of a hierarchical page table, right? So rather than having one large page table for the whole address space, you split that up into multiple levels. And since you're doing binary arithmetic here, it's sort of easy, right? So you take a few upper bits and then the lower bits as a hierarchy, right? So you can have 4 upper level page table size page tables, and then which point to another directory entry, and so on and so forth. You can make it go as much as possible. So here's an example of a 2-level paging scheme, right? So you have 2 levels of paging scheme. That means now the page table will have this outer page table, which points to an inner page table, which points to your actual memory address, right? So when you have to do the translation, you first look to see where this entry has to be, the next level has to be. If it is invalid, that means the whole thing is not going to be there, right? But if it is valid, you follow that to this page table, which follows that to here. Of course, you can keep going as many levels as you want, right? So what's the cost of doing this stuff? What do you want to can you think of reasons why you would want to go 3, 4, 5? So for 64-bit architecture, right? So can we go to like 10 layers of stuff like this? You could go any number of levels you want and make the page table small, because essentially you're only allocating what you wanted, right? So what's the cost of going multiple levels?
Lookups, time lookup.
Yeah, so in the example before we said lookup could take 2 memory lookup, right? The more levels you go, the more memory you have to look up, right? So now you have to, if you want to translate one address, you have to do memory lookup for this page table, then memory lookup for this page table, then memory lookup for the data you want, right? So this, in the worst case, can take you 3 lookups, right? You can have, of course, TLBs, but TLBs are only a certain size, right? So TLB, now you have to use a TLB for this and this, right? And the interactions become very complicated, right? This TLB entry may be here, but you may be going through lots of the stuff. So again, it depends on how a particular application is running. But in general, the more levels you add, in the worst case, you may have to go through that many levels of memory lookup. So your system performance may degrade horrendously, right? So 2 is acceptable, considered acceptable. You don't tend to see more of those, and we'll see different ways of dealing with the, especially when you go to the 64-bit processor, right? So for folks who are doing architecture, 64-bit processors add lots of these annoying problems, right? For 32-bit, you can deal with them, sort of, at least right now. You couldn't deal with them back when they came out, right? Back when they came out, machines tend to have, let's say, 4 megs of main memory, right? It was not acceptable to say, you have 4 meg memory machine, I'm going to need 16 megabytes for page table, right? Because that's more than what you had. But right now, most of you have 1 or 2 gigabytes of main memory, so page table size is not a thing you worry about. Go to 64-bit, you're going to have a trouble, right? We can't do this stuff because we may have to have, like, let's say, 10 levels, which means that in the best case, you sort of go through a TLB hit in all of those. But in the most normal case, you'll do so many memory accesses that each instruction could run 10 times slower because it's doing all this memory lookup. And you don't want that, right? So essentially the way you would implement this is to for the page, you split them into multiple bits, and you say this is the outer bit. So you use this bits to figure out where the inner page table has to be, and use that to figure out where this address is, right? So this implements this graph, right? So more you take the same address, you play different games. Again, this is done by hardware, not by operating systems. Operating system does not define how many bits should go to each of those, right? But it's duty to fill up these tables. It's duty to make sure that all these entries are what they have to be, and you create this hierarchy of page tables. So it works for 32-bit architecture, not necessarily for 64-bit, right? So actually I have an example here. So if you have a P1, P2 for 2 level, you use the P1 to figure out which outer table you want, and use that to figure out what this table you want, and go to the actual data, right? So since those are, since you can't really go for too many levels, another hardware mechanism that is popular is the notion of a hashed page table, right? How many of you know the hashing data structure, right? You must have heard about it somewhere, right? So essentially, hashing data structure, you take an address, you hash it, right? If it's a unique one-way hash, then essentially you take a number, it'll give you something which is not necessarily unique, right? So if you give it 10, it may hash it to say 1. If you give it 20, it may hash it to 1, right? But the idea here is you go from something large to something small, and if you choose the hashing table well, then the number of collisions will be minimal, right? If you have a collision, you kind of have it as a linear structure to go through the stuff. So you can use that to do the same thing. So if you can do a hash, you assume that the P becomes a smaller number. You don't want to do a hash where the number becomes larger, right? So you hash it to a smaller number, such that this hash table will have to be smaller than for the original page table. The flip side of that is you will get collisions, right? The collisions are all stored as a linked list data structure. So in the worst case, it is possible that all the page table entries will hash into one long bucket, and then you'll have to do a sequential search. But if you do it right, then the hash collisions will be minimal, such that you will be able to work fine, right? Especially if you don't use all the P bits for your program, then you may find a good hashing function such that the collisions are minimal and you get good performance, right? It again depends on the hashing function. A good hashing function would let you reduce this hash table size without incurring too much cost, right? A bad hashing function would increase the complexity of the linear lookup here, right? And again, this is done by hardware. Again, this is done without our control. So we don't know how big that data structure has to be, how this hashing structure is, right? But essentially, we need to, if you use this structure, then you could potentially reduce the size of the hash table, the page table, which is the hash table in this construct, right? Again, you need to have hardware which performs this hashing function. It has to be fast, right? Because this is in the critical path. Every instruction will have to do this. So if you can do this in hardware, if you find a good hashing function, then this can be expected to reduce the page size, right? So, and the hardware manufacturers will have to figure out how typical programs access memory to figure out the good hashing function. A good hashing function which will not have too many collisions, and a good hashing function which can be implemented easily in hardware is what they want, right? So, here's another assignment for the hardware folks, right? If you can do that, then we can reap the benefit. This can potentially be smaller, but again, that's a challenge. That's one way to go, right? So in the best case, so if you can do the hashing function, let's say instantaneously, then this may be a good thing if you don't have too many collisions. If you have too many collisions, you have to pay the cost for the hashing function. You have to do a lookup on the hash table, and then you have to search through all the collision entries, right? Potentially sequentially, and that can be a slow thing, right? So the worst case, it can be very slow, but hopefully, if things are working fine, you should be able to go faster, right? Make sense? Again, these are techniques that the hardware folks can give you, and that will help us reduce the page table size, because Page table size is something that we as operating systems people would worry about, not the hardware folks. Right? Hardware folks are not really worried about how you manage these things. But without managing the page tables, you can't really run programs, so you kind of have to have a partnership. The last type, which is essentially what is used by 64-bit machines, right? 64-bit is such a big number, right? 64-bit, I think if you have 64-bit, I think the number of, I forget the exact number, but the number of atoms in the known universe is, I think, 2 power 72 or 2 power 73 or something like that, right? So 64-bit is a sufficiently large number. It's a really big number, right? 64-bit is, I don't know how to say that, but it's 16 times 2 power 60, right? No, not 60. It's a big, very big number, right? So you can't really play all this hashing. It just escapes me, but 2 power 10 is 1K, so it's a very big number, right? So you can't play this notion of hashing and all those things to address 64-bit, right? So what happened was, like, the very first generation of 64-bit machines you can buy were not really 64-bit, right? So you couldn't really access the 64 bits. So you were kind of left with, the first DEC alpha could only access like 40 bits and so on, right? So they were doing like not the whole 64-bit. Do you know why we went to 64-bit addressing? This is not operating system, it's the hardware stuff, right? Most of the machines you buy are 64-bit. Can you think of a couple of reasons why we want 64-bit? Yeah.
So you can address more than 4 gigs of memory?
Yeah, you can address more than 4 gigs of memory. You can now access this really large number, right? So you're not now tied to 4 gigs. So you can have a really large array, right? 4 gigs sounds like a lot of memory, but 4 gigs is not really that big because of the way we want. Right? So if you want to have really large arrays and if you want to have really big programs, 4 gigs you run into a problem, right? So you want to be able to access a lot of stuff, and it also helps you in terms of the data structure, right? If you have a 64-bit integer, right, then you can do a lot of operations almost in parallel, right? So you can operate on a bigger integer, you can operate on them faster. So 64-bit is something that the users really want, but the flip side is you go to 64-bit, you have to deal with the size of the page table, right? Which is so big that you will have to go to so many levels if you do a hierarchical stuff. So you're kind of forced to do something. And the one thing that they do is the notion of an inverted page table, right? Which is kind of a weird concept. So in every page table, what you have is the page table entry for every logical address, right? So every logical address, you have one entry which points to the physical address, right? So the page table size is really decided by the logical address, not by the physical address, right? So depending on how big you want the logical address, you have to have that much of a page table entry. The actual physical pages need not be as big as a logical address, right? So when I say 2 power 64, if I want to do it that way, since the address space can be up to 2 power 64, I will have to have a page table which can store that much of a content, right? What I do in the inverted page table is I flip it, right? Now it no longer holds the logical address, but it holds the physical address, right? So this page table now holds the physical, there is one entry for each physical page, right? So theoretically, the logical address space can be equal to the physical address space. So if you ever get that big a memory, right? I don't know, 16, quadrillion, kind of like a really big number, then you'll run into a problem, right? But most normal machines, we still have maybe terabyte or something, right? Which is still way smaller than what the address can do. So the logical address space is a lot bigger than what the physical address space is. So if I do an inversion, then I only have to find a page table entry which will hold for each physical address. And the nice thing is, I need to have only one table for all the processes, right? Because it only maps to the physical address. So as long as the physical address does not change when I do a context switch, I need to have this one table, right? So that's the good thing. The table only needs to be as big as the physical memory you have, and we don't have that much memory anyway, so we are kind of okay. The bad thing is We are trying to translate it the other way. We are trying to translate it where I have the logical address. Now I want to find out what the physical address is. I'm not doing this. So the table is going to store for this physical address space, what is the logical address which is stored there. And I'm looking for, I have a logical address. What's the physical page I'm looking for? So I change it such that the table is now smaller, but the complexity is I need to search for it. So this is what happens, right? So I take forget the PID for a moment. So now I have a page table which corresponds to all the physical address pages, right? It stores so this means that on physical frame I, because it's the I offset from here, I has the logical address P, right? And I'm looking for P. Ignore the PID for a moment, right? I'm looking for P, right? So before I could look at the P, find the Pth element, and find whatever it is, and I'm done. Here I have to search through this table to find out which element has P as a second value, and whichever it is, then I know this I is the offset. So I take I and put it and get the address. Does that make sense? So I have to do a search. I have to search this table, not me, but the hardware. The hardware has to search this table to find out what it's looking for, right? And you can imagine all kinds of search you can think of, right? You can have it sorted, you can have it, linear search and what have you. Let's say linear search, right? Linear search means that you have to go through each of these address elements to come to what you want, right? In the worst case, linear search would search all the way across this table. So if you have, depending on how much physical memory you have, this happens to be 16 megabytes, right? In the worst case, you'll have to search through the whole table to find what you're looking for, right? And searching for the whole table is awful because this is in memory, right? So the hardware has to look up for this address, see if it matches P. No, look up for this address, look up for this address, look up for that, right? All the way here. So the worst case, you're basically running a little memory lookup program inside your hardware, and you can find what it's looking for, right? And you need this PID because you just need this one table for the entire system. You don't need to change it for different. So now processors don't have to have one. You need only one per hardware per machine because the physical address is the same, right? You can use it across multiple processors by essentially giving it a PID, and the hardware now has to support that every address will have to have this ID identifier. It does not matter what it is, but it's some identifier. So it will make sure that the identifier that you're requesting is the same as what is here, right? Otherwise, you may end up using. So it is possible for another PID here, another entry, to have a different PID for the same P here, right? Because another process may have the same logical address. So this P is not unique, but PID and P is unique, right? Does that make sense? It's kind of a weird way of looking at it, but essentially you kind of flip it around. So now the table can no longer be larger than what the physical address is, right? And now you can have only one table for the whole operating system, which is really good. So now you can have one page table for all the processors, and it's not that big. So if you buy more memory, this will become bigger, but that's it, right? The complexity is you have to search through the stuff. And that's where all the hardware will have to go, right? So now you need as much TLB as possible. You basically, so ideally you would like this to be in a cache, right? You like this whole table to be in a cache, and you can't. So however close you can get to that is where you get the performance, right? So when you go to 64-bit, if you do inverted page table, I don't know exactly how much complexity you would put on this component, but essentially, if you don't solve this, your machine will be a dog, right? Because if you have to look up for every address, every time I have to access a variable, if I have to search through these things, right? In the worst case, if the entry happens to be here, right? If my program has to go through all the stuff to figure out where the mapping is, my system will be so slow that you wouldn't want to use a 64-bit machine, right? So you have to make this faster. So if you took a course on architecture, this is probably one of the techniques you want to learn. How to do this inverted page table such that you can get good performance, right? The answer here is you have to have cache, right? Obviously, that's the only thing we can do. And you have to have some kind of cache which will avoid searching through the stuff, right? And of course, that is bounded. Of course, that's linked to how you program, right? All this is linked to how you program. So if you write awful programs which access all over the place, right? Access addresses all over the place, which is, we'll call that in the next chapter locality of reference. So if you are a good program which asks memory which is sort of near where you were asking before, right? Then you keep a locality very well. So if you're asking stuff which are closer in memory, if the locality is maintained, that means you're likely to keep asking the same entry here. That means it's likely to be cached. That means you're likely to be getting good performance. If you write a program where you randomly access memory all over the place, right? So if you implement a matrix multiplication algorithm where you randomly pick a row and randomly pick a column, you multiply, add it, and then you do random stuff, right? So you randomly do the stuff, right? Your performance will be so bad, you'll think that something is wrong, right? So you can try on any of the modern machines. If you can take a multiplication where you go through the row by row, multiplication is kind of weird because one way you go row by row, and the other matrix you go by column, right? So if you're a really good programmer, you want lots of matrix multiplication, you will rearrange this matrix to be in a certain way where you can get good memory performance, right? But regardless, the first matrix you go row by row, second matrix you go by column, which is bad. But if you want to really make it bad, randomly pick a row, randomly pick a column, calculate it, then randomly pick another row, randomly pick another column, calculate it. Try that program, right? On the 64-bit machines, it'll be so slow because you're essentially going and searching through this stuff. It'll take 100,000 of times slower, right? And there's nothing the hardware can do for you. There's nothing the operating system can do for you. You as a programmer will notice it, and you're noticing it because you're dealing with the inverted page table. Right? So those are three different ways of doing the stuff, and depending on what the hardware gives you, we can do that. And essentially, when you go to 64-bit architecture, there's not a whole lot of options left because there's such a big data memory space. You are forced to go to inverted page table whether you like it or not, right? And the only thing you can do is you can add larger and larger TLB caches to make this thing go faster. But if you wrote a program which tries to fight against the TLB, then you'll reap the benefit of running such a program, right? Oh, so one last topic I'll kind of mention is the notion of a shared page table, right? So since the operating system links the page in a page table, right? Sharing between two processes is very easy, right? So if I want something to be shared between two processes, all I have to do is I have to put the same page in the page table for both the processes. Then both of them can access the same thing, right? And we'll get back to this and we can do more interesting stuff, right? But for now, if both of them are accessing the same page, all I have to do is add this entry into the page table for both the processes. So when any of them access it, you can get that, right? And it's used a lot actually for programs, especially if you write position independent code, right? If you write code where you access variables which are relative to where you are, then it's position independent, and it's very good to be used in a situation like this. So essentially what happens is, in a typical system, you may have multiple processes. All of them use the same libraries, right? All of them use, like, let's say, the C library or what have you. So you have one copy of C library, right, which is mapped into all these processes, because all you need to do is, like, for example, if you look at ED1, ED2, ED3, right? All the processes have it, right? So this process has ED1, ED2, ED3, and data 2. This one has ED1, ED2, ED3, data 3, right? And let's say the ED1, ED2, ED3 is like a libc. Everybody wrote C program. So what will happen is the page table for all of them will point to the same physical address, 346. They'll have a different for data, right? So even though you're running three programs, they're all accessing the same physical page, but they don't know that because all they do is access through the page table. Operating system makes sure that the page table entries are the right ones, right? So they're all accessing as if it belongs to them, but ED1 and 2 and 3 is shared by all these three. And in this case, if you're doing as a text, you don't modify it, say you're okay. And we can do much more complicated stuff as we proceed. But essentially, this is a way to share stuff. So that's one of the reasons why you can run more and more programs which are larger and larger, seemingly larger and larger. So if you run PowerPoint and Word, if you look at the memory size, PowerPoint may look like it's taking, half a gig, and Word may look like it's taking half a gig. But really, they can both run on a machine which has only half a gig because they share a lot of this stuff, right? So in this case, you only need that many pages to run all these three programs, even though each one of them think they have this whole ED1 for themselves, right? So we'll stop at that. We'll take the segmentation notion after the exam. So like I said, I'll be gone. If you send a chat or email, I should check it when I'm on the road. I'll try to go online, but most likely I'll check chat and stuff. So see you guys next Monday.